There is something around you now that has been there since before you were born. It extends outward from the ground beneath your feet, reaching thousands of miles into space, wrapping around the planet in gentle arcs that follow no visible path. You cannot see it. You cannot feel it against your skin. It makes no sound, casts no shadow, and asks nothing of your attention. Yet it has been here, constant and unannounced, through every moment of human history, and long before that, before cities, before language, before the first breath of any living thing that would one day learn to wonder about invisible forces. This is Earth's magnetic field. It is not a barrier in the way a wall is a barrier, not a shield in the way armor is a shield. It is more like a current flowing through water, or the way warmth spreads through a room without being directed. It exists because the planet exists, because deep within the Earth, metal moves in slow, perpetual circulation, heated by pressures and temperatures that belong to another scale of experience entirely. That movement, sustained across billions of years, creates this field. The field shapes space around the planet, bends the paths of particles traveling from the sun, and quietly influences systems so vast and so small that most of them pass unnoticed. You have lived your entire life within this presence. So have your parents and theirs, and every generation stretching back to the beginning of what we call humanity. The magnetic field was here when the first cells divided into ancient oceans. It was here when mountains rose and wore away. It was here during the long ages when nothing observed it, when there were no eyes to see and no minds to wonder. It simply was, as it has always been, a byproduct of planetary motion, a consequence of heat and metal and time. But imagine, for a moment, that this presence begins to fade, not suddenly, not in a flash or a tremor or a single catastrophic event, but slowly, across thousands of years, thinning like morning mist under a rising sun. The field does not collapse all at once. It weakens, it shifts, its boundaries blur and wander. The forces that have held it in place for so long begin to lose their coherence, and the invisible architecture that surrounds the planet begins to soften, to dissolve, to become something less defined than it once was. This is not a story of a sudden disaster. It is a story of gradual transformation, unfolding across a scale of time that resists human comprehension. 1,000 years might pass, and nothing would seem different. Another 1,000, and still the sun would rise and set, the oceans would move with the moon, and life would continue in forms recognizable to those who came before. But beneath the surface of that continuity, something fundamental would be changing. The planet would be losing one of the oldest features it possesses, one of the defining characteristics of its relationship with the space around it. And in that loss, slowly and without announcement, Earth would begin to become something else. This is not a narrative that demands urgency. It is not a warning or a prophecy. It is simply an exploration of what it might mean for a planet to lose something it has carried for so long. What happens when an invisible presence, taken entirely for granted, begins to fade? What shifts occur in the systems that depend on it, even if those systems never knew they were depending on anything at all? And what does a world look like when the field that once shaped its interaction with space is no longer there to bend the paths of particles, to guide the solar wind, to hold a certain kind of order in place? These questions do not require answers delivered with speed or certainty. They are meant to be held gently, turned over slowly, explored without the pressure of conclusion. They invite you to imagine a process so gradual that no single generation would ever perceive it as a change, yet so profound that over deep time, the planet itself would be altered in ways both subtle and vast. The magnetic field is not alive. It does not think or intend. It has no awareness of its own existence, no sense of purpose or direction. It is simply a pattern that emerges from the motion of molten iron deep within the Earth's core, sustained by heat that has been radiating outward since the planet first coalesced from dust and gas. That pattern extends outward, creating loops and arcs that stretch into space, deflecting charged particles, guiding them around the planet rather than allowing them to strike the surface directly. It is a consequence of physics, nothing more and nothing less. And yet, for all its impersonal nature, it has been a constant companion to this world, shaping the conditions that allowed life to emerge and persist. To imagine its loss is to imagine a world slowly becoming more exposed, more open to the forces of space. Not vulnerable in the way a living thing is vulnerable, but changed in the way a landscape is changed when a river shifts its course. The planet would continue. The sun would still provide warmth and light. The moon would still pull the tides, but the relationship between Earth and the space around it would be different. Quieter in some ways, less mediated, more direct. And so, we begin here with the simple recognition that this field exists, that it has always existed within the span of human memory, and that its presence has shaped this world in ways we are only beginning to understand. We begin with the understanding that it could fade, that such fading would take thousands upon thousands of years, and that the process would be so slow that it would feel, to anyone living through it, like nothing at all. This is not a story of catastrophe. It is a story of transformation across deep time. It is a meditation on what it means for a planet to change, to lose something fundamental, and to continue nonetheless. It is an invitation to drift through these ideas without needing to resolve them, to let them unfold at their own pace, as the magnetic field itself has unfolded across the lifetime of this world. There is no urgency here, only observation, only the slow consideration of what has been, what might be lost, and what remains when the familiar begins to fade. Deep within the earth, far below the surface where life moves and breathes, there is motion. Not the sudden jolt of earthquakes or the explosive force of volcanoes, but a slower, more persistent kind of movement. One that operates on a scale measured not in seconds or hours, but in centuries and millennia. This motion belongs to the outer core, a vast layer of molten iron and nickel, heated to temperatures that would vaporize anything familiar, pressurized by the weight of thousands of miles of rock above it. This metal is not solid. It flows, circulates, rises and falls in currents that span the width of continents, driven by heat rising from the even hotter inner core below. This is where the magnetic field begins. Not as an intention or a design, but as a natural consequence of this motion. When liquid metal moves, and when that metal is electrically conductive, it generates magnetic fields. The faster the motion, the stronger the field. The more complex the circulation, the more intricate the patterns that emerge. And because the Earth rotates, because it spins steadily on its axis once every 24 hours, these currents are twisted, shaped, organized into something that resembles order. This is the geodynamo, a self-sustaining system where motion creates magnetism, and magnetism influences motion, a feedback loop that has persisted for billions of years. The field that emerges from this process is not uniform. It does not extend outward from the planet in a perfect sphere. Instead, it forms loops, great arcs that stretch from one magnetic pole to the other, bending through space in sweeping curves that guide and redirect the charged particles streaming outward from the sun. These are not physical structures. They are invisible lines of force, patterns in space that can only be detected through their effects. Iron filings sprinkled near a magnet will align themselves along these lines, revealing their shape. In the same way, particles in space, electrons, protons, ions of hydrogen and helium, follow the contours of Earth's magnetic field, spiraling along these invisible pathways rather than traveling in straight lines. The sun is always emitting particles. This is the solar wind, a constant outpouring of charged matter that streams across the solar system at speeds of hundreds of kilometers per second. When these particles encounter Earth, they do not strike the planet directly, not in the way a stone strikes water. Instead, they encounter the magnetic field first. The field deflects them, bends their paths, channels them around the planet and toward the poles, where some of them eventually interact with the upper atmosphere, creating auroras, those shimmering curtains of green and red light that appear in the skies near the Arctic and Antarctic. The auroras are visible evidence of an invisible process, a reminder that the magnetic field is always there, always working, always guiding particles away from the surface. This interaction is not a conflict. It is not a battle between Earth and space. It is simply what happens when moving charges encounter a magnetic field. There is no resistance in the way a solid object resists force. The particles do not slow down or stop. They simply change direction, following the paths the field creates for them. And the field itself is not depleted or weakened by this interaction. It continues as it always has, shaped by the motion of metal thousands of miles below, utterly indifferent to the particles it redirects. The magnetic field extends far beyond the atmosphere, far beyond the satellites that orbit the planet, stretching outward for tens of thousands of kilometers before it finally blends into the background magnetic field of the Sun itself. This region of influence is called the magnetosphere. It is not a sphere because the solar wind pushes against it, compressing the field on the side facing the Sun and stretching it into a long tail on the opposite side. The magnetosphere is constantly shifting, expanding and contracting in response to fluctuations in the solar wind, but it never disappears. It is always there, a vast invisible envelope that surrounds the planet and mediates its relationship with space. Within this envelope, the conditions are different from the space beyond it. Particles that would otherwise travel freely are trapped, held in place by the field, accumulating in regions called the Van Allen belts, zones of concentrated radiation that encircle the Earth. These belts are not dangerous to life on the surface, but they are a reminder that the magnetic field does more than deflect particles. It also captures them, holds them, creates environments that would not exist without its presence. The magnetic poles are not fixed. They wander, drifting slowly across the surface of the planet in response to changes in the flow of molten metal far below. Sometimes they move a few kilometers per year. Sometimes they move faster, dozens of kilometers annually, responding to shifts in the currents that generate the field. This wandering is normal. It has been happening for as long as the field has existed, and occasionally, over timescales measured in hundreds of thousands of years, the poles reverse entirely. North becomes south, south becomes north. The field does not disappear during these reversals, but it does weaken, sometimes significantly, as the internal currents reorganize themselves into a new configuration. These reversals leave evidence in the geological record. When lava cools and solidifies, the magnetic minerals within it align themselves with the Earth's magnetic field at that moment, preserving a snapshot of the field's direction. By studying these ancient rocks, scientists have mapped the history of the field's reversals, discovering that they happen irregularly, with no predictable pattern. Sometimes hundreds of thousands of years pass between reversals, sometimes millions. The last one occurred about 780,000 years ago. The next one could happen tomorrow, or it could happen a million years from now. The planet does not operate on a schedule, but reversals are not the same as loss. During a reversal, the field weakens and becomes more complex, with multiple poles appearing and disappearing, but it does not vanish. The geodynamo continues. The molten metal continues to circulate. The field eventually stabilizes again, and life on the surface continues without interruption. What we are imagining now is something different, not a temporary weakening or reorganization, but a gradual, sustained decline, a fading that does not reverse itself, a thinning that continues across ages until the field is no longer strong enough to shape the space around the planet in the way it once did. This is not impossible. Other planets have lost their magnetic fields. Mars once had one, billions of years ago, generated by the motion of molten metal in its core. But Mars is smaller than Earth, and it cooled more quickly. The currents in its core slowed and eventually stopped, and the magnetic field faded. Today, Mars has no global magnetic field, only weak, localized patches of magnetism in its crust remnants of a system that once functioned as Earth's does now. The atmosphere of Mars, no longer protected by a magnetic field, was gradually stripped away by the solar wind, leaving the planet with a thin, cold shell of gas barely 1/100th the density of Earth's atmosphere. Earth is larger, its core is hotter, its geodynamo is more vigorous. But it too is cooling, slowly radiating heat into space, and one day far in the future, but inevitable nonetheless, the motion within the core will slow, the currents will weaken. The magnetic field will begin to fade, not because of any external force, but simply because the internal engine that generates it is running down. This is not a process that can be halted or reversed. It is not something that technology or intention can prevent. It is a consequence of the finite heat contained within the planet, heat that has been escaping since the Earth first formed, and that will continue to escape until the core is cold and still. That day is unimaginably far away, measured in billions of years, but it will come. And long before the core becomes truly cold, long before the geodynamo stops entirely, the magnetic field will begin to weaken, to thin, to lose its coherence. What would that weakening look like? Not to instruments or satellites, but to the planet itself. What changes when the invisible presence that has always been there begins, slowly and without announcement, to fade? Imagine a process so slow that it cannot be perceived. Not in a single lifetime, not in 100 lifetimes, not even in 1,000. Imagine a change unfolding across tens of thousands of years, each year contributing a shift so small that no instrument could measure it, no observer could detect it, no system could respond to it in any immediate way. This is the kind of change we are considering. Not a collapse, not a rupture, but a thinning so gradual that it feels, at any given moment, like nothing at all. The magnetic field does not disappear overnight. It does not flicker out like a candle in the wind. Instead, it weakens incrementally, losing strength in a process that mirrors the cooling of the Earth's core itself. The currents of molten metal that generate the field begin to slow, not because anything has broken, but simply because the heat driving those currents is slowly, inevitably radiating away. The geodynamo continues to operate, but with less vigor. The field it produces becomes weaker, its loops extending less far into space, its influence over charged particles diminishing year by year. For the first 1,000 years, perhaps nothing changes that anyone would notice. The auroras still dance in the polar skies. The magnetosphere still deflects the solar wind. Navigation systems that rely on magnetic compasses still function as they always have. Life continues in all its forms, utterly unaware that the invisible architecture surrounding the planet is beginning to soften. But after 10,000 years, the field is measurably weaker. Not gone, but diminished. The magnetosphere, once extending 60,000 kilometers into space on the sunward side, now reaches only 50,000. The difference is invisible, but it means that the boundary between Earth's magnetic influence and the solar wind has moved closer to the planet. Particles that would once have been deflected farther away now approach more closely before being turned aside. The Van Allen belts, those zones of trapped radiation, begin to lose their sharpness, their boundaries becoming less distinct as the field weakens and particles begin to leak away. After 50,000 years, the weakening becomes more pronounced. The magnetic poles, always wandering, now drift more erratically, their paths less stable as the currents beneath them lose coherence. The field's shape becomes more irregular, less symmetrical, with regions of stronger and weaker magnetism appearing across the planet's surface. Some areas retain more protection than others, not by design, but simply as a consequence of the increasingly chaotic flow of molten metal below. The magnetosphere compresses further, its boundary now only 40,000 kilometers from Earth on the sunward side, and the long tail that stretches away on the opposite side becomes shorter, less organized. The auroras change. They become more frequent, appearing at lower latitudes than before, as particles that would once have been deflected far from the planet now penetrate deeper into the magnetosphere before being guided toward the poles. The lights in the sky grow brighter, more vivid, spreading across regions where they were once rare. This might seem beautiful to those who witness it, but it is a sign of weakening, not strength. The field is losing its ability to keep particles at a distance, and the atmosphere is beginning to interact more directly with the solar wind. After 100,000 years, the field is perhaps half as strong as it once was. The magnetosphere is now compressed to 30,000 kilometers, and its structure is increasingly unstable, fluctuating more dramatically in response to surges in the solar wind. During periods of high solar activity, when the sun releases bursts of particles in events called coronal mass ejections, the magnetosphere is pushed even closer to the planet, sometimes compressing to within 20,000 kilometers of the surface. These are not sudden disasters, but they represent a new state of vulnerability, a condition where the boundary between Earth and space is less clearly defined. The Van Allen belts, once stable zones of trapped radiation, begin to disperse. Particles that would have been held in place for years now escape more easily, streaming down toward the atmosphere or drifting away into space. The radiation environment around the planet changes, becoming less predictable, more variable. Satellites in orbit, if there are still satellites in orbit, experience increased exposure to radiation, their electronics degrading more quickly, their operational lifetimes shortened. And still, on the surface, life continues. The weakening of the magnetic field is not an immediate threat to biology. Plants still grow, animals still migrate, ecosystems still function. The sun still provides the energy that drives photosynthesis. The oceans still regulate the planet's temperature. The atmosphere, though beginning to change, still contains the oxygen and nitrogen that complex life requires. But the processes that shape the atmosphere are starting to shift, subtly and without announcement, as the interaction between the upper atmosphere and the solar wind becomes more direct. After 200,000 years, the field is perhaps a quarter of its original strength. The magnetosphere is now compressed to within 20,000 kilometers on the sunward side, barely extending beyond the orbits of the highest satellites. The field structure is fragmented, with multiple weak poles appearing and disappearing across the surface. None of them stable, none of them dominant. The concept of north and south magnetic poles becomes less meaningful, as the field no longer organizes itself into a clear dipole pattern. Compasses, if anyone still uses compasses, begin to behave erratically, pointing in directions that change from year to year, from decade to decade. The auroras are now a constant presence at mid-latitudes, visible even in regions that once saw them only during extreme solar storms. They are no longer rare or remarkable. They are simply part of the sky, a nightly display of greens and reds and purples, beautiful and unceasing, a visible manifestation of the fact that the atmosphere is now interacting more directly with space than it has in billions of years. The upper atmosphere begins to heat. This is not a dramatic warming, not something that would be felt on the surface, but a consequence of increased exposure to the solar wind. Charged particles that would once have been deflected now strike the atmosphere more frequently, transferring their energy to the gases there, causing them to become more energized, more agitated. This heating causes the atmosphere to expand slightly, its outer layers reaching higher into space, where they are even more exposed to the solar wind. And in that exposure, they begin, very slowly, to be carried away. This is not a process that happens quickly. The atmosphere is vast, containing trillions of tons of gas, and losing even a small fraction of it takes immense amounts of time. But the process has begun. Atoms and molecules in the upper atmosphere, energized by collisions with solar particles, begin to move fast enough to escape the planet's gravity. One by one, they drift away into space, lost to the void. The rate of loss is measured in tons per year, perhaps at first, a negligible amount compared to the total mass of the atmosphere. But the process is cumulative. Year after year, the atmosphere becomes fractionally thinner. And unlike the magnetic field, which could, in principle, recover if the geodynamo were to strengthen again, the atmosphere cannot easily reclaim what has been lost. The atoms that escape do not return. After 500,000 years, the magnetic field is perhaps a tenth of its original strength, if it can still be said to have a coherent structure at all. The magnetosphere is barely distinguishable from the surrounding space, its boundary fluctuating wildly, sometimes pushed back to within 10,000 kilometers of the surface during solar storms. The planet is now, in a meaningful sense, unshielded. The solar wind interacts directly with the upper atmosphere, stripping away gases at an accelerating rate. Not because the wind has strengthened, but because the field that once held it at bay is no longer there to do so. And still, on the surface, the change is subtle. The sky is still blue during the day, though perhaps a slightly different shade of blue, the result of a thinner atmosphere scattering light differently. The nights are still dark, though the auroras are now visible from almost every latitude, a permanent feature of the sky. The temperature at the surface has not changed dramatically, not yet, because the atmosphere is still thick enough to retain heat, still massive enough to regulate the planet's climate. But the trajectory is clear. The atmosphere is thinning. The protection it offers is diminishing, and the process, once begun, does not easily stop. This is the gradual softening of the invisible shield. Not a dramatic failure, but a slow, persistent decline, unfolding across timescales that dwarf human history, reshaping the planet in ways that are imperceptible in any single moment but profound across the span of ages. The magnetic field is fading, the atmosphere is beginning to follow, and the planet, indifferent to these changes, continues its orbit around the Sun as it always has, as it always will. The atmosphere does not have a clear boundary. It does not end at a specific altitude where air becomes space in a single, definable transition. Instead, it fades gradually, thinning with height, becoming less dense, less substantial, until at some point, hundreds of kilometers above the surface, there are so few molecules per cubic meter that the concept of air loses meaning. What remains is not quite the atmosphere and not quite space, but something in between, a region where the last traces of Earth's gases mingle with the charged particles of the solar wind. This is the exosphere, the outermost layer of the atmosphere, where the pull of Earth's gravity is weak enough that individual atoms and molecules can, if they are moving fast enough, escape into space. This has always been happening. Even with a strong magnetic field, even with the full protection of the magnetosphere, Earth has always been losing atmosphere, bit by bit, atom by atom. But the rate of loss has always been slow, balanced by other processes: volcanic outgassing, the release of gases from the interior, the gradual recycling of materials through the biosphere. The atmosphere has remained, on balance, stable. But as the magnetic field weakens, as the magnetosphere compresses and fragments, the balance begins to shift. The solar wind, no longer held at a distance, begins to interact more directly with the upper atmosphere. This interaction is not violent. It does not strip the atmosphere away in great gusts or waves. It is more like erosion, a persistent, patient process that works over millennia, removing small amounts of material continuously, never stopping, never slowing. The solar wind consists of charged particles, protons, electrons, and heavier ions, traveling at high speeds, carried outward from the Sun by the energy of magnetic fields and plasma dynamics. When these particles encounter the upper atmosphere, they collide with atoms and molecules there, transferring energy. Some of these collisions are gentle, merely jostling the atmospheric particles, heating them slightly. But some collisions are more energetic, imparting enough speed to the atmospheric atoms that they reach escape velocity, the speed required to break free of Earth's gravity. These atoms do not fall back. They drift upward, away from the planet, joining the flow of particles streaming through the solar system. At first, the rate of loss is small, perhaps a few hundred tons of atmospheric gas per day, most of it hydrogen and helium, the lightest elements, the ones most easily accelerated to escape velocity. This is not a noticeable amount. Earth's atmosphere has a total mass of about 5 quadrillion tons, and losing a few hundred tons per day would take hundreds of millions of years to make a significant difference. But as the magnetic field continues to weaken, as the magnetosphere compresses further, the rate of loss increases. A few hundred tons per day becomes 1,000, then 10,000. The process accelerates, not because the solar wind has changed, but because the atmosphere is now more exposed, more accessible, more vulnerable to the steady outflow of particles from the Sun. Oxygen, heavier than hydrogen, is harder to strip away, but it is not immune. Given enough energy, even oxygen atoms can be accelerated to escape velocity. Nitrogen too, carbon dioxide, water vapor, all the gases that make up the complex chemistry of Earth's atmosphere. All of them, under the right conditions, can be lost to space. And over tens of thousands of years, then hundreds of thousands, then millions, the cumulative effect becomes significant. The thinning of the atmosphere is not uniform. The upper layers thin first, because they are the most exposed, the least protected by the mass of air below. The exosphere, once extending several thousand kilometers above the surface, contracts, its outer boundary moving closer to the planet as the gases there are carried away. The thermosphere, the layer below, also thins, its density decreasing as particles are lost faster than they can be replaced. And as these upper layers thin, the boundary between atmosphere and space moves downward, bringing the direct effects of the solar wind closer to the surface. The auroras, once confined to the polar regions, now appear at all latitudes, even near the equator. They are no longer rare events triggered by solar storms, but a constant feature of the night sky, visible whenever the sun is below the horizon. The lights shimmer and ripple, greens and reds and purples, beautiful and silent. A reminder that the atmosphere is now in direct contact with space in ways it has not been for billions of years. But the auroras are not just a light show. They are evidence of energy being deposited into the atmosphere, energy that heats the gases there, making them expand, making them more vulnerable to further loss. The process is self-reinforcing. As the atmosphere thins, it becomes easier for the solar wind to penetrate deeper. As the solar wind penetrates deeper, it strips away more gas. As more gas is lost, the atmosphere thins further. The cycle continues, each stage feeding the next, not rapidly, but with a steady, patient persistence that operates across geological timescales. Water vapor, one of the most important gases in Earth's atmosphere, is particularly vulnerable. Water molecules in the upper atmosphere can be broken apart by ultraviolet radiation from the sun, splitting into hydrogen and oxygen. The hydrogen, being light, escapes easily. The oxygen, being heavier, lingers longer, but it too can eventually be lost. Over time, this process removes water from the planet, not just from the atmosphere, but from the entire hydrological cycle. The oceans, vast as they are not infinite. Lose enough water vapor to space, and the oceans themselves will begin to shrink, slowly over millions of years, their surfaces lowering, their volumes decreasing, the planet's total inventory of water diminishing. This has happened elsewhere in the solar system. Venus, which likely once had oceans, lost them. The water vapor in its atmosphere was broken apart by sunlight, the hydrogen escaped, and what remained was a thick, hot atmosphere of carbon dioxide with barely a trace of water left. Mars, too, lost its water, though it had a magnetic field once. When that field faded, the atmosphere thinned, and the water that had once flowed in rivers and pooled in lakes either froze beneath the surface or was lost to space. Earth, with its still strong magnetic field, has retained its water, but if that field were to fade, the same processes would begin here. The conversation between the atmosphere and space is not a dialogue. The atmosphere does not speak or respond. It simply reacts to the forces acting upon it, losing particles when they are energized enough to escape, retaining them when they are not. And the solar wind does not listen or adjust. It simply flows, constant and indifferent, carrying away whatever it encounters. This is not a conflict, not a struggle, but an interaction that has always been happening and that will continue to happen, the only variable being the strength of the magnetic field that mediates it. As millennia pass, as the field weakens further, the interaction becomes more direct, more efficient at stripping away the atmosphere. The rate of loss climbs from tons per day to tons per second. The atmosphere, once so thick that it scattered light into a brilliant blue sky, begins to thin to the point where the sky becomes darker, less vibrant, the scattering less effective. The pressure at the surface begins, very slowly, to decrease, dropping from its long stable value of about 1 atmosphere. The pressure we define as normal to something slightly less, not enough to be felt in a human lifetime, but measurable over thousands of years. And, as the pressure decreases, the boiling point of water decreases as well. At 1 atmosphere of pressure, water boils at 100 degrees Celsius. At lower pressures, it boils at lower temperatures. Eventually, if the pressure drops far enough, liquid water becomes unstable on the surface. It either freezes or evaporates, and if it evaporates, it joins the gases in the atmosphere, where it is vulnerable to being broken apart and lost to space. The oceans, which have been stable features of Earth for billions of years, would begin, over immense timescales, to shrink. This is not a process that unfolds in centuries or even millennia. It takes millions of years, perhaps tens of millions, for atmospheric loss to reach the point where the surface pressure drops significantly. But the process, once begun, is difficult to stop. The magnetic field, the primary defense against this loss, is weakening. And unlike the atmosphere, which can, in principle, be replenished by volcanic activity or impacts from comets, the magnetic field cannot easily recover. Its strength depends on the geodynamo, on the motion of molten metal in the core, and that motion is slowing as the core cools. The trajectory is clear, even if the timescale is vast. So the upper air continues its long conversation with space, a one-sided exchange where the atmosphere gives and space takes, where particles drift away and do not return, where the boundary between planet and void becomes less distinct with each passing age. The process is silent, it is invisible, it requires no witnesses. And it continues, patient and inevitable, as the magnetic field fades and the planet slowly becomes more open to the forces beyond it. The sun is not just a source of light and heat. It is also a source of radiation, electromagnetic energy spanning a vast spectrum, from the long wavelengths of radio waves to the short, energetic wavelengths of X-rays and gamma rays. Much of this radiation is harmless, or at least manageable. Visible light warms the surface and drives photosynthesis. Infrared radiation heats the ground and the oceans, but some wavelengths are more dangerous. Ultraviolet radiation, especially the shorter wavelengths in the UVB and UVC range, can damage biological molecules, breaking apart DNA, disrupting cellular processes, causing mutations and cell death. And beyond the ultraviolet, there are even more energetic forms of radiation. X-rays, gamma rays, cosmic rays, that can penetrate deeply into matter, ionizing atoms, creating reactive particles that cascade through tissues and materials, leaving trails of damage in their wake. Earth's atmosphere and magnetic field have always worked together to protect the surface from these forms of radiation. The magnetic field deflects charged particles, cosmic rays, solar protons, bending their paths so that they spiral toward the poles or miss the planet entirely. The atmosphere absorbs much of the ultraviolet radiation, particularly in the stratosphere, where ozone molecules capture UVC and UVB photons, preventing them from reaching the surface. Together, these two systems have maintained conditions on the surface that are hospitable to life, shielding organisms from the most harmful forms of radiation, allowing complex chemistry to persist without being constantly disrupted by high-energy photons and particles. But as the magnetic field weakens, this protection begins to erode. Particles that would once have been deflected now reach the atmosphere more easily. Cosmic rays, high-energy protons, and atomic nuclei, traveling through space at nearly the speed of light, begin to penetrate deeper into the atmosphere before colliding with air molecules. These collisions create showers of secondary particles, pions, muons, electrons, that cascade downward, some of them reaching the surface. The intensity of cosmic rays at ground level increases, not dramatically at first, but measurably, incrementally, year by year. For life on the surface, this increased radiation is a persistent, low-level stress. It does not kill organisms outright, not in the way a sudden burst of radiation might, but it increases the rate at which DNA is damaged, at which mutations occur, at which cells must expend energy to repair the constant, subtle harm inflicted by high-energy particles. Plants, animals, microorganisms, all of them experience this increase, though they do not perceive it, do not understand it, and cannot, in any immediate sense, respond to it. They simply continue, generation after generation, their genomes accumulating mutations at a slightly higher rate than before. Some of these mutations are neutral, neither beneficial nor harmful. Some are harmful, reducing the fitness of the organisms that carry them, making them less likely to survive and reproduce. And some, very rarely, are beneficial, providing new traits that happen to be advantageous in the slowly changing environment. Over thousands of generations, these mutations shape the evolution of life, steering it in directions that are impossible to predict, creating new forms and eliminating old ones, all in response to the quiet, persistent pressure of increased radiation. Ultraviolet radiation, too, begins to increase at the surface. The ozone layer, which depends on a delicate balance of chemical reactions driven by sunlight, begins to thin as the upper atmosphere is stripped away by the solar wind. Ozone molecules are constantly being created and destroyed in the stratosphere, and as the density of the stratosphere decreases, the rate of ozone production decreases as well. The layer becomes thinner, less effective at absorbing UVB and UVC radiation. More of this radiation reaches the surface, where it affects everything exposed to sunlight. Plants are particularly vulnerable. Their leaves, broad and flat to maximize the capture of visible light, are also maximally exposed to ultraviolet radiation. At low levels, plants can tolerate UV, producing protective compounds and repairing damaged tissues. But as UV levels increase, the damage accumulates faster than it can be repaired. Leaves become discolored, their photosynthetic efficiency decreases, and growth slows. Some species, those with better UV tolerance or the ability to produce more protective pigments, fare better than others. Others, less tolerant, begin to decline, their population shrinking, their ranges contracting. The oceans, too, are affected. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web, live in the uppermost layer of the ocean, where sunlight penetrates. They are adapted to current UV levels, but as those levels increase, their productivity declines. Some species are more sensitive than others, and as the sensitive species decline, the composition of the phytoplankton community shifts. This has cascading effects up the food web, affecting the zooplankton that eat the phytoplankton, the fish that eat the zooplankton, and so on, all the way to the largest marine predators. The changes are gradual, unfolding over thousands of years, and they do not result in immediate, widespread extinctions. Life is adaptable, capable of adjusting to changing conditions through evolution, migration, and shifts in behavior, but the adjustments are not without cost. Ecosystems become less productive, less diverse, less stable. Species that were once common become rare, habitats that were once rich become sparse, and the overall resilience of the biosphere, the ability of life to recover from disturbances, to maintain its complexity and diversity, begins to decline. Radiation also affects non-living systems. Materials exposed to increased UV radiation degrade more quickly. Plastics become brittle and crack. Paints fade. Fabrics weaken. In a world with human technology, this would mean more frequent maintenance, more frequent replacement of materials, more energy and resources devoted simply to counteracting the effects of increased radiation. But in a world without human civilization, or one where human presence has faded, these effects are simply part of the background, part of the slow transformation of the surface environment. The surface itself changes too, though subtly. Rocks exposed to increased UV radiation undergo different weathering processes, their minerals breaking down at different rates. Soils, affected by changes in plant cover and microbial activity, shift in composition. Deserts might expand as plants struggle to survive increased UV exposure. Forests might thin, their canopies becoming more open, allowing more light and more UV to reach the forest floor. Grasslands might shift towards species that grow low to the ground, minimizing their exposure to direct sunlight. And yet, the planet remains recognizable. The sky is still above, the ground still below. The sun still rises and sets. The seasons still cycle, driven by the tilt of Earth's axis and its orbit around the sun. The changes in radiation levels are real, but they do not transform the planet into something utterly alien. They simply nudge it in a new direction, altering the balance of life, the chemistry of the atmosphere, the processes that shape the surface. At night, the stars are brighter. With a thinner atmosphere, there is less scattering of light, less distortion, and the stars appear more numerous, more vivid. The Milky Way, that faint band of light across the sky, becomes more pronounced, a river of stars stretching from horizon to horizon. The auroras, now visible at all latitudes, add their own shifting colors to the night. Greens and reds dancing across the sky, a constant reminder of the interaction between the planet and space. This is a world where the boundary between Earth and the cosmos is less distinct, where the protective layers that once insulated the surface have thinned, where radiation and particles from space reach the ground more easily. It is not a dead world, not yet, but it is a world under stress, a world where life must adapt to conditions that are subtly but persistently harsher than those that prevailed for billions of years. The magnetic field is fading, the atmosphere is thinning, and the surface is becoming a place where survival requires new strategies, new tolerances, new forms. Life does not have a plan. It does not look ahead, does not anticipate, does not prepare for changes that have not yet occurred. It exists in the present, shaped by the conditions that surround it, responding only to the immediate pressures of survival and reproduction. When the environment changes, life changes with it, not because organisms choose to adapt, but because those individuals that happen, by chance, to possess traits suited to the new conditions are more likely to survive and pass those traits to the next generation. This is evolution, not as a deliberate process, but as a consequence of variation, selection, and time. As the magnetic field weakens and the surface is exposed to more radiation, as the atmosphere thins and UV levels increase, life on Earth begins to shift. Not all at once, not in a single dramatic transformation, but slowly across thousands and millions of years as generation after generation responds to the changing conditions. Some species thrive, others decline, some migrate to new habitats, others go extinct. The overall pattern is one of continuous adjustment as the biosphere reconfigures itself to match the new environment. Plants are among the first to feel the effects. Their dependence on sunlight makes them vulnerable to increased UV radiation, and as UV levels rise, many species experience stress. Leaves develop more protective pigments, compounds that absorb UV light before it can damage the photosynthetic machinery within the cells. These pigments often appear as reds, purples, or browns, and forests that were once dominated by green foliage begin to take on different hues, their canopies tinged with darker colors as plants invest more resources in UV protection. But not all plants can adapt quickly enough. Species that are slow to reproduce, that produce few offspring, that have limited genetic variation, these species struggle. They produce fewer seeds. Their seedlings have lower survival rates. Their populations shrink, and they retreat to refugia, small pockets of favorable habitat where conditions are less harsh. Over time, if the stress continues, these species may disappear entirely, leaving behind ecosystems that are less diverse, less complex. Other plants, particularly those in open, sun-exposed environments, evolve new strategies. Some become smaller, growing low to the ground where they are partially shielded by rocks or other vegetation. Some develop thicker cuticles, waxy coatings on their leaves that reflect UV radiation. Some alter their life cycles, flowering and setting seed more quickly, minimizing the time they're exposed to the most intense sunlight. These adaptations are not innovations in the sense of new inventions, but rather the selection of existing variations, traits that were always present in the population, but that only become advantageous under the new conditions. Animals, too, must adapt. Many animals depend on plants for food, and as plant communities change, so do the animals that eat them. Herbivores that specialized on plants now in decline must shift to new food sources or face starvation. Some succeed in making this shift, discovering that other plants, perhaps less preferred but more abundant, can sustain them. Others fail, their populations dwindling as their preferred foods disappear. Carnivores, higher up the food chain, face their own challenges. As herbivore populations fluctuate, predators must adjust their hunting strategies, their territories, their reproductive rates. Some predators are generalists, capable of eating a wide variety of prey, and these species fare better in the changing environment. Others are specialists, finely tuned to hunt specific prey, and these species struggle as their targets become scarce. In the oceans, the effects are similar. Phytoplankton communities shift as some species tolerate increased UV better than others. Zooplankton that depend on the declining species must find new food sources. Fish that depend on those zooplankton face leaner times. Entire food webs reorganize, with some species becoming more abundant and others nearly disappearing. Coral reefs, already sensitive to changes in temperature and water chemistry, face additional stress from increased UV radiation. Corals bleach more frequently, expelling the symbiotic algae that provide them with energy. Some reefs recover, others do not, their structures slowly eroding, becoming rubble, their vibrant ecosystems collapsing into simpler, less productive states. Migration becomes more common. As conditions in one region become less favorable, species move, seeking environments where survival is easier. Birds shift their ranges, following the changing distribution of food and nesting sites. Mammals migrate to higher latitudes or higher elevations, where temperatures are cooler and UV exposure is slightly less intense. Fish and marine mammals follow shifting ocean currents and changing patterns of productivity. These migrations are not sudden or coordinated. They happen gradually, over many generations, as individuals at the edges of a species range gradually push into new territory, while populations in the old range decline. But not all species can migrate. Plants, rooted in place, cannot move except through the slow dispersal of seeds. Species that live on islands or in isolated habitats have nowhere to go. Species that require highly specific conditions, a particular temperature range, a particular type of soil, a particular community of other organisms, find fewer and fewer places where those conditions exist. These species are the most vulnerable, the most likely to disappear as the environment continues to change. Extinction, when it comes, is quiet. There is no announcement, no moment when a species is officially gone. Instead, populations shrink, their ranges contract, and eventually the last individual dies, leaving no offspring. The species is simply no longer present. Over thousands of years, as the stress from increased radiation accumulates, as ecosystems continue to shift, the rate of extinction increases. Not to the level of a mass extinction, not to the point where the majority of species disappear, but enough that the biosphere becomes noticeably less diverse, less complex, less rich in the variety of forms that once filled every available niche. And yet, new forms arise. Evolution does not stop. Even as some species go extinct, others diversify, filling the niches left vacant, adapting to the new conditions, radiating into new forms. Life has survived worse. It has endured ice ages, asteroid impacts, volcanic eruptions that blanketed the planet in ash and altered the climate for centuries. The loss of the magnetic field, the thinning of the atmosphere, the increase in radiation. These are challenges, but they are not insurmountable. Life adapts. It finds a way, not because it is clever or determined, but simply because that is what life does. It persists. It varies. It fills the available space. Microorganisms, in particular, are resilient. Bacteria and archaea, with their rapid reproduction and vast genetic diversity, adapt quickly to changing conditions. Some species develop enhanced DNA repair mechanisms, allowing them to survive higher levels of radiation. Others retreat underground to caves and aquifers where they are shielded from UV and cosmic rays. Still others form symbioses with larger organisms, providing them with compounds that protect against radiation in exchange for nutrients. The microbial world, invisible to the naked eye, continues its silent work, breaking down organic matter, cycling nutrients, maintaining the chemical balances that allow larger organisms to survive. Insects, too, are adaptable. Their short generation times and large populations mean they can evolve quickly in response to changing conditions. Species that are sensitive to UV decline, but others, perhaps those with darker pigmentation or different behaviors, thrive. The composition of insect communities shifts, and with it, the patterns of pollination, herbivory, and decomposition that structure terrestrial ecosystems. Over millions of years, the biosphere reconfigures itself. The planet is still green, still teeming with life, but the specific forms that life takes are different. Forests are dominated by different species, grasslands support different communities. Oceans are less productive, but still home to a wide variety of organisms. The overall biomass of the planet might be lower, the total amount of living matter reduced by the stresses imposed by increased radiation and a thinning atmosphere, but life persists, as it always has, adapting to whatever conditions the planet provides. There is no judgment in this process, no sense of loss or gain. Life does not mourn the species that go extinct. It does not celebrate the new forms that arise. It simply continues, driven by the fundamental processes of reproduction, variation, and selection, responding to the environment without intention or awareness, moving at its own pace, indifferent to the timescales of human concern or the vast, slow changes unfolding in the planet's physical systems. Humanity, if it still exists in this distant, altered world, would find itself living under conditions subtly but significantly different from those that prevailed during the rise of civilization. The sky would look different. The stars would be brighter, the auroras constant, the sunlight carrying more UV radiation. The atmosphere would be thinner, the pressure at the surface measurably lower, the air containing less oxygen than it once did. These are not conditions that would end human life immediately, but they would shape it, constrain it, demand adaptation. The first challenge would be radiation. With the magnetic field weakened and the ozone layer thinned, the surface would be exposed to higher levels of UV and cosmic rays. For people living outdoors, under open sky, this would be a constant hazard. Skin cancer rates would rise, cataracts would become more common, immune systems would be weakened by the ongoing damage to cells. Lifespans might shorten, not dramatically, but enough to be noticeable, enough to shift the age structure of populations and the strategies they use to survive. People would adapt, as they always have. Clothing would become more protective, covering more of the body, made from materials that block UV radiation. Buildings would be designed to provide more shelter, with thicker walls and fewer windows, or with windows made from materials that filter out harmful wavelengths. Agriculture would shift toward crops that can tolerate higher UV levels, or crops that are grown under protective covers, shielding them from direct sunlight. Entire patterns of daily life might change, with more activity occurring at night or during twilight hours, when the sun is lower in the sky and UV levels are reduced. Technology would be crucial, if it still exists. Societies capable of maintaining advanced technology could develop artificial magnetic fields, localized shields that protect cities or agricultural areas from cosmic rays and solar particles. They could manufacture synthetic ozone, releasing it into the stratosphere to replenish the thinning layer. They could engineer crops with enhanced UV tolerance, or develop pharmaceutical treatments that repair radiation damage more efficiently. But all of these measures would require resources, energy, and a level of social organization that might be difficult to sustain in a world where environmental stresses are slowly accumulating. And if technology fails, if the systems that support advanced civilization break down due to resource depletion, conflict, or simply the passage of time, humanity would be left with simpler strategies. Migration, perhaps, moving populations to regions where conditions are more favorable, higher latitudes, higher elevations, underground. Adaptation through culture, developing knowledge and practices that minimize exposure to radiation, that maximize the use of available resources, that allow communities to survive in an environment that is less forgiving than the one their ancestors knew. Population sizes might decline. With increased radiation, decreased agricultural productivity, and the cumulative stresses of a changing environment, the carrying capacity of the planet, the maximum population it can sustainably support would be lower than it once was. Communities would become smaller, more dispersed, more reliant on local resources. The dense, interconnected networks of trade and communication that characterize modern civilization might fragment, replaced by more isolated, self-sufficient groups. But human civilization, in some form, could persist. It has survived ice ages, droughts, plagues, and collapses before. The loss of the magnetic field, as profound as it is, would unfold slowly enough that each generation would have time to adapt, to pass on knowledge, to develop new strategies. The world would be harsher, but not uninhabitable. The sky would be different, but still beautiful. The challenges would be greater, but not insurmountable. And yet, there is another possibility, that humanity, faced with the slow, inexorable decline of the planet's habitability, might choose to leave. Not immediately, not in a single dramatic exodus, but gradually, over centuries or millennia, as technological capacity develops and the risks of staying become clearer. Settlements on the Moon, on Mars, in orbital habitats. These might become not just experiments or outposts, but the primary homes of future generations, places where the environment is controlled, where radiation can be shielded, where the thinness of the atmosphere is irrelevant because there is no atmosphere to begin with, only sealed habitats filled with air and life. In such a future, Earth would be left behind, not as a dead world, but as a quieter one, a place where life continues in simpler forms, where the absence of human civilization allows other processes to unfold unimpeded. The cities would empty, their structures slowly crumbling under the forces of weather and time. The roads would crack and be overgrown. The fields would return to wild vegetation, and the domesticated animals would either adapt to life without human care or perish. The planet would continue, as it always has, with or without witnesses. But even if humanity remains, even if it persists on the surface, adapting and enduring, there would be a sense of loss. Not loss of specific things, but loss of the conditions that made certain kinds of life, certain kinds of civilization, possible. The ease with which crops once grew, the abundance of fresh water, the stability of the climate, the protection offered by the invisible field that once wrapped around the planet. All of these would be diminished, and the effort required simply to maintain a stable existence would be greater. This is not a narrative of heroic struggle or tragic downfall. It is simply an acknowledgement that the conditions for life on Earth are not permanent, that the systems that have supported complexity and diversity for so long are themselves subject to change, and that change, when it comes, does not wait for readiness or consent. It simply unfolds, patient and inevitable, and those who inhabit the changing world must adjust or fade. Human civilization, in this altered world, would be smaller, quieter, more cautious. It would carry the memory of a time when the planet was more hospitable, when the magnetic field was strong and the atmosphere thick, but it would also carry the knowledge that survival is possible even when the old certainties are gone. It would be a civilization shaped by scarcity and radiation, and the constant, low-level awareness that the planet is no longer what it once was. And perhaps, in that quieter world, there would be a different kind of beauty, the beauty of simplicity, the beauty of communities that know each other well, that rely on each other completely, the beauty of a sky filled with stars, unobscured by light pollution or atmospheric haze, where the auroras dance every night and the Milky Way stretches across the heavens like a reminder of the vastness beyond. A world where humanity is smaller but still present, still observing, still wondering about the forces that shape existence. Imagine a time far beyond the era we have been considering, a time when the weakening of the magnetic field has run its full course, when the atmosphere has thinned to a fraction of its former density, when the conditions on the surface are no longer recognizable as the ones that prevailed during the age of complex life. This is not a dead planet, not a cold, airless rock like the moon, but it is a profoundly altered one, a place where the familiar has been replaced by something quieter, sparser, more austere. The sky is no longer blue. With so little atmosphere remaining, there is insufficient scattering of sunlight to produce the brilliant azure that once defined daylight. Instead, the sky fades from a pale, washed-out color near the horizon to a deep, almost black expanse overhead, where the stars are visible even during the day, pinpoints of light against the darkness. The sun is harsh and bright, its light unfiltered by the thick layers of air that once softened it. Shadows are sharp and absolute, and the contrast between light and dark is extreme. The surface is cooler than it once was, not because the sun has dimmed, but because the thin atmosphere can no longer retain heat effectively. Without a substantial blanket of gases to trap infrared radiation, the warmth absorbed during the day radiates back into space at night, and surface temperatures swing wildly between day and night. In some regions, the temperature might reach a comfortable level during the day, but at night it plunges far below freezing. This diurnal cycle is no longer moderated by atmospheric circulation or the heat capacity of thick air. It is driven almost entirely by the direct relationship between the surface and the sun, with little buffering in between. The oceans, once covering more than 70% of the planet's surface, have shrunk. Over millions of years, water vapor has been lost to space, hydrogen stripped away by the solar wind, oxygen slowly following. What remains is a smaller, shallower body of water, saltier than before, its volume reduced by a significant fraction. Some ocean basins are now dry, their floors exposed to the harsh sunlight, crusted with salt and minerals left behind as the water evaporated or drained away. The remaining oceans are still home to life, but it is a sparse, simplified form of life, dominated by microorganisms, with few complex organisms remaining. Rivers still flow, fed by what little precipitation still occurs, but they are smaller, less numerous, more seasonal. Many of the great river systems have dried up entirely, their beds now empty channels winding through barren landscapes. Lakes too have mostly disappeared, leaving behind playas and salt flats, vast empty spaces where water once pooled. The hydrological cycle, once vigorous and complex, is now a pale shadow of what it was, driven by the limited moisture remaining in the thin atmosphere. Vegetation is sparse. The plants that survive are those capable of tolerating extreme UV radiation, low atmospheric pressure, and the wide temperature swings between day and night. They grow slowly, conserving resources, clinging to life in sheltered locations, valleys, caves, the shaded sides of cliffs. There are no forests, no grasslands, only scattered patches of hardy, low-growing species, their leaves dark with protective pigments, their roots reaching deep into the soil in search of moisture. Much of the land is bare rock and sand, shaped by wind and the occasional rainstorm, but otherwise still and quiet. Animal life is even more scarce. The large, complex animals that once roamed the planet are gone, unable to survive the loss of habitat, the decline in plant productivity, the increase in radiation. What remains are small, simple forms, insects perhaps, and other arthropods, some reptiles, creatures that can burrow underground during the day to escape the harsh sunlight and the cold of the night. They emerge during twilight when conditions are more tolerable to feed and reproduce. Their populations are small, their distribution patchy, and many species that once existed are now extinct. The biosphere as a whole is smaller, less diverse, less productive. The total mass of living organisms on the planet is a fraction of what it once was. The intricate food webs, the complex interactions between species, the rich ecosystems that once covered the land and filled the oceans, all of these have simplified, pared down to their most essential elements. Life persists, but it is life on the edge, clinging to a planet that is no longer optimized for its survival. Yet the planet itself continues. The geological processes that have shaped Earth for billions of years do not depend on the magnetic field or the atmosphere. Plate tectonics still operates, driven by the heat within the Earth's mantle, though more slowly now as the planet continues to cool. Volcanoes still erupt, releasing gases that briefly thicken the atmosphere before they are carried away by the solar wind. Earthquakes still occur, reshaping the surface, creating new mountains, opening new valleys. Erosion continues, though it operates differently now, driven more by wind and less by water, sculpting the rocks into new forms. The planet's rotation continues, unchanged by the loss of the magnetic field. The day is still 24 hours long, the year still 365 days. The seasons still cycle, driven by the tilt of Earth's axis, though the differences between them are less pronounced now that the atmosphere is so thin. The moon still orbits, still pulls the tides in the remaining oceans, still lights the night sky with its reflected glow, and the auroras still appear, though they are different now. With the magnetic field gone, the solar wind interacts directly with the upper atmosphere, and the auroras are no longer confined to the polar regions. They are visible at all latitudes, vast, shimmering curtains of light that ripple across the sky whenever the sun releases a burst of particles. They are beautiful, but they are also a reminder of what has been lost, a visible sign that the planet is no longer shielded, no longer protected, no longer the same world it once was. In the deep underground, where radiation does not penetrate and temperature is stable, life may persist in more complex forms. Caves, aquifers, the spaces between rocks deep within the crust. These are refugia, places where conditions have changed less dramatically, where microorganisms and perhaps even small multicellular organisms can survive. They live in darkness, feeding on chemical energy rather than sunlight, part of a biosphere that is completely disconnected from the surface, unaware of the changes that have occurred above. This is Earth after the familiar, not dead, but profoundly altered. A planet that still has air, though not much, that still has water, though less than before, that still has life, though it is sparse and simple. A planet that continues to orbit the sun, to rotate on its axis, to exist as a physical system, even though the conditions that once made it a haven for complex life are gone. It is a quiet world. The sounds of wind and rain are less frequent. There are no animal calls, no rustling of leaves, no crash of ocean waves on a shoreline, just the silence of vast, empty spaces, broken occasionally by the groan of shifting rock or the hiss of wind-blown sand. It is a world that has aged, that has passed through the vibrant phase of its existence and entered a longer, quieter phase, one that will persist for billions of years until the sun itself begins to change and brings new transformations. This is not an ending, it is a transition, a passage from one state to another. The planet does not cease to exist. It simply becomes something else, something less familiar, something that bears the marks of time and change. And in that transformation, there is a kind of continuity, a reminder that nothing is permanent, that all systems eventually shift and alter, that the universe moves forward regardless of what is lost along the way. There is no moment when the story ends, no point at which the processes described here reach completion and stillness. The planet does not pause to acknowledge what has occurred. It does not reflect on the loss of the magnetic field, the thinning of the atmosphere, the simplification of life. It simply continues, as it has always continued, driven by forces that operate beyond intention or awareness. Deep within the Earth, the core still radiates heat, though less than before. The mantle still convects, carrying heat upward, driving the slow movement of tectonic plates across the surface. The planet is cooling, and it will continue to cool for billions of years, but that cooling is so gradual that it might as well be eternal. The changes it brings are measured not in lifetimes or centuries, but in geological epochs, vast stretches of time that dwarf anything experienced by living beings. The sun rises each day over a surface that is quieter than it once was. Light falls on bare rock and sparse vegetation, heating the ground, creating the sharp contrasts of shadow and brilliance that define this altered world. The stars wheel overhead at night, the same constellations they have always formed, though now they are visible with a clarity that was impossible when the atmosphere was thick and full of moisture. The Milky Way is a river of light, so dense with stars that it seems almost solid, a reminder that Earth is a small place within a much larger cosmos. The solar wind continues to flow outward from the sun, carrying charged particles into the space between the planets. It encounters Earth's thin atmosphere, stripping away atoms and molecules, carrying them into the void. This process will continue for as long as the sun shines, for billions of years into the future, slowly eroding what remains of the atmosphere until there is nothing left but the barest trace of gas clinging to the surface. But that endpoint is still unimaginably far away, separated from the present by spans of time so vast that contemplating them induces a kind of vertigo. Life, where it remains, continues without interpretation. The organisms that survive do not understand that they are living in an altered world, that the conditions they experience are different from those that prevailed in the past. They simply exist, responding to the immediate demands of survival, reproducing when conditions allow, dying when they do not. There is no narrative of loss or adaptation, no story they tell themselves. There is only the ongoing process of being alive, of metabolizing energy, of maintaining the complex chemistry that defines living systems. Underground, in the deep refugia where life has retreated, microorganisms continue their slow work. They break down minerals, extract energy from chemical gradients, recycle the elements that make up their bodies. They form communities, ecosystems that are invisible and unknown, that have no connection to the surface, no awareness of the changes that have occurred there. They exist in a timeless present, a state of being that has no beginning and no end, only continuation. The planet does not require witnesses. It does not need observers to validate its existence or to record its changes. It simply is, turning through space, orbiting the sun, aging slowly, transforming quietly. The loss of the magnetic field is one event among many in its long history, significant only in that it marks a transition from one state to another. There have been other transitions. There will be more. The planet will continue to change, to evolve, to become something different, and it will do so with or without life, with or without complexity, with or without anything resembling the world that once existed here. In the stillness of this altered world, there is a kind of peace, not the peace of endings, but the peace of continuity, The recognition that the universe does not stop, that processes continue, that time unfolds regardless of what is lost or gained. The magnetic field faded, the atmosphere thinned, life simplified, and the planet remained. It is different now, but it is still here, still orbiting, still turning, still existing within the flow of time. And perhaps, somewhere in the distant future, new processes will begin. Perhaps the core will cool enough that the geodynamo stops entirely and the planet becomes fully still, its magnetic field gone forever. Perhaps the sun will begin its transformation into a red giant, expanding, heating the inner planets, evaporating what remains of Earth's atmosphere and oceans, rendering the surface molten once more. Perhaps, in the far, far future, the planet will be consumed by the dying sun, its matter returning to the stellar plasma from which it originally formed, completing a cycle that began billions of years ago. But those possibilities are distant, abstract, separated from the present by timescales that resist comprehension. For now, for ages yet to come, the planet continues. The stars shine overhead, the sun rises and sets, the rocks weather and reform. And in the quiet spaces where life still clings, the processes of metabolism, reproduction, and evolution continue, slow and patient, indifferent to the vastness of time. There is no need for resolution, no need for the story to conclude. The planet does not end. It simply is, and will continue to be, for as long as the sun provides the energy that drives its surface processes, for as long as the internal heat supports its geological activity, for as long as the atoms that compose it remain bound together by gravity. This is Earth without the familiar, without the magnetic field that once defined its relationship with space, without the thick atmosphere that once cradled life, without the complexity that once filled its surface. But it is still Earth, still a planet, still a system of processes and forces that continue to operate, that have no need for recognition or understanding, that simply unfold one moment after another across the immense expanse of geological time. And so the world continues, quiet and persistent, beneath an open sky, beneath the stars, beneath the indifferent light of the sun, moving forward without pause, without reflection, without needing witnesses to validate its existence or to mourn what has been lost. It simply is, as it has always been, as it will always be, until time itself brings new transformations.